going to be moving to a new position at NEID Lab in August, though, and my talk today is on the NEID GTO survey. So as, do I advance? There we go. As you've all heard a lot now, NEID is it's a new EPRV spectrograph on the 3.5 meter wind telescope at Kitt Peak. It's a fiber-fed shell spectrograph, and the wavelength coverage is about 380 to 930 nanometers. Or as Paul said, it spans from the calcium H and K lines through the calcium infrared triplet. And importantly, and Doug talked about this a little bit on Monday too, NEID is available to the whole community through NEID Lab and the NN-Explore program. So it was designed as a community EPRV resource, and for the most part, that is how it has been used. But in addition to that, there's also a moderate amount of time that has been set aside, or about 300 hours per year, or 30 nights per year, a GTO program that is managed by the NEID science team. The main component of the GTO is the NEID Earth Twin Survey, or NETS, and this is a dedicated search for low mass, long period planets, or Earth twins, Earth analogs, around a sample of about 40 stars that we've been observing. Our team is also interested in using this survey to analyze and calculate detection sensitivity limits and occurrence rates. So we've adopted a somewhat algorithmic observing strategy to better facilitate this. So the strategy, we start with a broad, roughly uniform coverage that spans each star's observing season. That's shown by these blue points here. Each point would be a scheduled observation. We add a set of densely sampled observations every other night or so to facilitate stellar activity mitigation. We learned a lot about the importance of getting dense coverage to do that. And then we get a couple points on either end of each star's observing season as the star is either rising or setting. And this helps reduce annual aliasing effects, which can be a big problem and pretty important for that can cloud the detection of long period planets, the sort that we are interested in. So that's what we intend to do. NEID is a queue-based instrument, though, so we can't execute the strategy exactly as intended. Instead, we have to assign each set of observations to a queue priority within the observing framework that NEID operates under. And Sarah Logston has a really nice poster that describes NEID queue operations if you're interested in learning more about that. So our full idealized schedule will look something like this, where each row here is a different star in our sample, and then each of those points is one of these scheduled observations. And the different colors here correspond to the different queue priorities that we're using. This is the ideal schedule, of course, for a single year of observations. And here is what we actually did in the first year. So we can compare these two by looking at the intended windows, which I've shown with those color shaded regions, and seeing where our points fall relative to those. And you can see that we get a pretty good approximation of the intended strategy by using those queue priorities and scheduling in that framework. And this is, of course, made possible by the NEID queue, which allows us to observe on any night that NEID is on sky, rather than a limited set of nights or half nights as other instruments might face. So there were a few holes in our schedule. We did lose a few weeks last May due to some instrument issues. And then, of course, there was the Contreras fire, which set us back quite a bit. But if we just look at all the data we got, we did get quite a bit of data for most of these stars, which is starting to build a really nice, large data set with this EPRV instrument. And then we did get back on sky last November. So here's everything we've gotten in year 2 of operations for the NEID GTO survey. I won't harp on the fire too much, but I do just want to give a huge thanks to everyone in Tucson and at NEID Lab that helped ensure a safe shutdown and subsequent recovery of the instrument so that we could keep doing this and we weren't severely impacted by the fire. So we got a lot of data. And here is, I'll show a few diagnostics of that data. The first one I want to show is the RMS from the first year of data for all of our target stars. And each bar here is the RMS for a single star. The gray bars are stars without any known companions, stellar or planetary. The gold bars are stars with stellar companions, and blue is the known planets in the sample. I'm not going to talk about the stellar companions. Mark Giovanazzi actually has been doing some really cool work with combining Gaia astrometry to the precise NEID data to better understand those stars and their orbits. And I'll point you to his poster if you're interested in learning about those. But if we clean out the known planets from the sample, we can see that for almost all of the NEID GTO target stars, we're achieving an RMS of below 2 meters per second. There's only a few stars with RMS values above this level. This doesn't mean these stars are, this doesn't mean that NEID is showing scatter at the 2 meter per second level. But what we're seeing here is actually these are stars that we thought were among the quietest out there and still have some intrinsic level of scatter at this level, or known or unknown undetected planets at this level. So there are a few stars that are above this level, though. The first I want to point out is HD 26965. That's the star with the most astrophysical scatter in our sample. You've heard a few things about this star earlier this week. A few people gave talks on it. Just want to highlight this star has a detected strong periodicity at 41 days. That's consistent with the rotation period, as well as with peaks in the calcium HK and H alpha time series, as we've seen. And by my last count, I talked to a lot of people this week. I think there's 5 papers in prep that use our NEID data set to try to understand this signal a little bit more and also validate different methods for analyzing and better studying stellar variability. Jacob Lund also has a poster on this if you want to check it out. I think this is different from the poster he's giving a talk on later today, though. So some of these stars, the scatter is dominated by stellar activity or stellar variability. But for others, we're starting to find new planets. So this is HD 86728. There's a published planet candidate signal by Leah Hirsch in 2021 using CPS data. They found a planet candidate at 31 days, and that signal pops out really easily very early on in our NEID data. So this is the periodogram of our NEID time series. We see that peak at 31 days very easily. So we did a little bit of digging, looked into the signal. It's very well fit by a Keplerian. We see that the periodicity drops out in the residuals. So this is our Keplerian fit to the NEID data, as well as some data from APF. The APF archival data is really useful because it helps us better anchor the ephemeris of the orbit. It's got a much longer time series there. And here's a phase folded NEID plus APF. And we can see that, so the blue histograms and distributions on the right-hand side there, that's the NEID only fit, and then red is NEID plus APF. You can see that with that longer time series, APF really helps us nail down the orbital period. It tightens those constraints quite a bit. But most of the power for the other parameters is driven by NEID, especially for the semi-amplitude here. You can see that NEID submeter per second precision does a great job of nailing down that, despite the much shorter baseline and much smaller sample of data than these past instruments that weren't getting submeter per second precision. Going back to the RV fit and the residuals for a second, we can see that while there is no periodic power in the residuals, there is still some astrophysical scatter there at the 1 to 2 meter per second level. We want to make sure that so this is astrophysical scatter, not driven by this planet. That could be another planet, it could be something else, it could be stellar variability. We want to make sure that stellar variability isn't driving the fit, and this isn't just some ephemeral signal that isn't actually a Keplerian planet. So we look at the periodicity for all of our activity indicators. We don't see anything there. And then just to make sure, I run a Gaussian process regression using Christian Gilbertson's GLOM code. And we can see that the NEID with GLOM, which is the black error bars on that point, are pretty consistent with the Keplerian only fits. So we're pretty confident this is a planet and not driven by anything else. The last thing I want to touch on today is the fact that after the instrument restart, we expect there to be a break in the RV time series. There's going to be some offset between the RV 0 point we measure before the restart and after the restart. This is something that has been seen for a lot of instruments that have gone through cooldowns and warmups and other sorts of instrument interventions. So for the GTO sample, I've been trying to calibrate what this offset is so far. Still a work in progress because we still are building up our post-restart data set and the number of points we need to actually calibrate this robustly. But so far, it looks like we're measuring this at a pretty consistent level at about 7 meters per second. For all stars, the pre minus post time series median is about 7 meters per second to within uncertainties. So if we look at this as a function of spectral type and temperature, we can see that there's no trends here either. This is something that we might expect, given that the RV information content for different stars will depend on where their temperature is, and that will affect what we measure the offset to be. But we don't see any trends for most spectral types. Here I'm showing the boundaries between the CCF masks that our pipeline uses. And again, there's no stark differences between the different masks until we take a look at our single M dwarf in the sample. This is a GJ411. It's the only M dwarf in the GTO sample. And we see that this has a much lower offset than the rest of the stars. A strong caveat here, of course, is that GJ411 has a known long period planet, and the offset that we're measuring could be degenerate with the trend introduced by the planet. So this isn't a strong result yet, but we are going to look into this a little bit more, look at some other M dwarfs and try to figure out whether or not there really is a smaller offset for the M dwarfs than for the rest of the stars. But for the rest of the sample, this is really nice because it allows us to use the measured offset here as somewhat of a prior for other stars that might have data from before and after the offset that are at lower precision or that don't have quite as many data points, where it'll be harder to calibrate that offset with just those stars accurately. So to wrap up, I just want to go back to this plot showing the RMS again, where we see that in year one, most of our stars have measured RMSs of below 2 meters per second. And again, emphasize the fact that this isn't scattered from the instrument. I mean, to some extent it will be. We are getting photon noise particles of about 30 centimeters per second. But above that level, this is astrophysical. It could be stellar variability. It could be unknown planets. And the only way to figure out which it is to do more detailed analysis of stars like this. So I want to plug the Splinter session this afternoon that's led by Belinda Nicholson, Jacob Lund, and Lily Zhao, which is about using targeted observations of certain stars to better understand stellar variability signals so that we can actually dig below this level and see what's coming up. Yeah, I'm still have a little time left, so I'll walk through my summary slide then. First point, the NEID Earth Twin Survey, or NETS, is a dedicated EPRV exoplanet survey that's looking for long period signals. Second is that EPRV data sets like this, as we saw with HG26965, can enable time-resolved analysis of stellar variability signals that will allow us to see things that we couldn't have seen before with instruments at lower precision or at lower cadence. And then, yeah, NETS very easily recovers known planet signals. So I was able to very easily fit out all of the known planets in our sample, and it can easily detect new planets that were inaccessible to surveys with the previous generation of spectrographs. I know this isn't something that's unique to NEID, but it is something that we can always look forward to with all of the EPRV spectrographs that have been discussed this week. And then the summer 2022 shutdown and subsequent restart introduced a 7 meter per second offset in the RV0 point that is mostly consistent for stars of spectral types for G and K dwarfs, possibly different for M dwarfs, but it is good to see that this is very easy to calibrate out. And then, yeah, last, even the quietest stars in our sample are intrinsically variable, and we have a lot of work to do to continue to understand those. So with that, thanks, and I'll take questions.
Arvind, I have a question. Maybe could you say a little bit about at what level you need to calibrate this offset? You said it's mostly consistent. To me, it looked like it was sort of plus or minus a meter per second, but you're looking for sub-meter per second signals. Do you have a sense, do we need to know it on the 10 centimeter per second level, the 1 centimeter per second level to not introduce an error?
Yeah, so I guess it depends on what signals we're interested in finding, right? So if I go back to this plot here, these error bars here are showing the pre and post restart RMS values. So the RMS is about a meter per second or so. We can't really expect to measure that offset to much better than what the RMS of the pre and post restart time series are. So as long as those RMSs are at the meter per second level, I don't think we can do much better. But if we are interested in finding signals at the 10 centimeter per second level, yeah, I do think that we need precisions at that level if these signals span multiple years of data. Yeah.
Yeah, I don't know if you said it, but I guess the reason for checking this for temperature is to see where the information is, right? Did you check the red and the blue part of your spectrograph? I mean, 8 meters per second is probably something that you could see in chunks of the spectral range already. So is the 0 point offset different at different wavelength ranges?
That is a really good question. That isn't something we've looked at yet, but that is, I mean, that's a great suggestion. I should look into what
that may explain the M dwarf offset, right?
Yeah. I don't know what the answer is, but I need to look into it.
All right, in the interest of